As mentioned in previous video, correlation only measures strength of association between two variables. But in practice, we need to evaluate association between one variable and a set of multiple variables. For example, the house price and other factors, IM and LSTAT. Secondly, in many applications, we not only need to evaluate the strength of association. For example, in stock trading in high frequency, we may need to estimate price change in next 5 seconds using information of price change, volume, etc. of the last 10 minutes. That is, we need to build an equation between one variable you try to estimate, called response, and other multiple variables, which you use to estimate response, called predictors. This equation is called models. The most widely used equation for this is a linear regression model. We use this model to estimate response variable, which is also called prediction. In this video, we will discuss a linear model using simplest version, simple linear regression model, in which it only has one predictor. From previous exploration, we have the scatter matrix for mutual pattern between variables. We can see that IM, number of rooms, as a predictor, has a very strong linear pattern with MEDV, which is the median value of a house price. This pair of variables is good for our introduction of a simple linear regression model. Just like in confidence interval estimation, we assume the population is normal. For linear regression, we also make assumptions about response and predictors in population. This is our starting point to build models. We assume that response variables in population are all normal. They have equal variance sigma squared. But the mean of a response variable is determined by predictors in linear form, mu I equal to beta 0 plus beta 1 times xi. Like in confidence interval estimation, we use samples to estimate population parameter mu. Similarly, we also use samples to estimate parameters of population beta 0, beta 1, sigma. In conclusion, if we apply linear regression model, we assume there exists such a real pattern in population. More specifically, linearity, the mean of y, is linearly determined by predictors. Independence, with different x, responses are independent. Normality, the random noise and y follow normal distributions. Equivariance, the variance of y are all equal, even if the values of predictors are different. These assumptions need to be validated if you want to make an inference using linear regression models. But in most cases, we do not need to be strict about these assumptions if you just use the model to make a prediction. In real application, we do not know beta 0, which is called intercept, beta 1, which is called coefficient or slope, and sigma neither. So we cannot identify exact position of a line of a mean equation. Instead, we have samples consisting of pairs of y and x, as shown in this scatter plot. They are not on a straight line, since the median price of a house is not only determined by number of rooms, it is also determined by location and other conditions of a house. Collectively, we put all other factors into noise term. It does not mean they are really noise, because we will consider their pattern with the house price in a simple linear regression model. We know that mean equation is a straight line. All the sample pair goes around this line because of the noise term. Using sample data, our target is to find a straight line y hat equal to b0 plus b1 times x, to approximate the mean equation as close as possible, where b0 is the estimated value of beta 0 and b1 is the estimated value for beta 1. This equation is called the prediction equation. The idea here is straightforward, but it has a problem. we are not sure which line is closest to main equation. Since we do not know the location of real main equation, hence we have to predict with other standard. Suppose we find a line with b0 equal to 1 and b1 equal to 2. We can build a prediction equation using Python. This prediction equation is our guess of main equation. Guess response is our estimated mean for response, which is also our guess or predict value for response. Then we can compute the difference between real median price and our guess, which we call observed error. We name it observed error to distinguish it from noise in population model. Observed error can be regarded as observed value of a noise term. Here we print out observed error for 7th, 20th, 100th pairs from the sample. Using massive sum of data frame, we can compute the sum of squared errors, in short, SSE. If SSE is larger, it is easy to figure out observed pairs stay far away from your predict equation. Ideally, we want to get a line whose SSE or sum of squared errors is very small. Alternatively speaking, all sample pairs are close to the predict line you found. Now it is turned into a minimization problem. Choose the best estimate values for beta 0 and beta 1 to minimize SSE term. The prediction equation found using this criteria is called best fit line. This process of estimation is called ordinary least square estimation. With mathematical computation, there exist explicit formulas for B0 and B1. From formula of B1, which is the estimate value for the slope of the model, the denominator is a measure of variation of predictor. The numerator is to measure the association between x and y. The ratio clearly is to measure sensitivity of a change of response with respect to the change of predictor. To estimate models, we have statistical package, stats models. We use method fit of the module OLS of stats models. Here, OLS stands for ordinary least square estimation. The parameter data gives the names of data frame of a sample. The parameter formula tells which columns of data frame are response or predictors. We can get estimated coefficients B0, B1 using feature parents of model. Finally, we can compute predict value using prediction equation. We can plot best fit line along with sample data and our initial guess. The yellow colored line is a best fit line. Obviously, some square error is much smaller with best fit line. Hence, the criterion using least squares is reasonable. Stats models also provide statistical evaluation of the model by using method summary. First, we need to pay attention p-value of slope. This p-value is a p-value for the two-tailed test of slope. As we discussed in topic 3 for population mean, in two-tailed test, p-value is to compute the probability for a statistic to take more extreme values on the two tails. Here, statistic is B1 minus beta 1 divided by SB1. Because population standard deviation for the estimate B1 is unknown, we use a sampled SD for B1 as a replacement, and hence this statistic follows a t-distribution with degree freedom n-2. The reason for degree freedom equal to n-2 is because we need the x bar and y bar to compute SB1, which causes the loss of two freedom. If we can reject the null, beta 1 is not equal to 0. It is equivalent to say that the predict RM is useful in predicting the median value of house, and we only have 5% chance to include RM in the model wrongly. Second, we can get a confidence interval for the slope. By default, confidence level is 95%. 95% confidence interval for the slope is 8.27 and 9.925. This interval is located on the positive side of real line. Hence, the slope is positive with high chance, which is consistent with correlation and the scatter plot of our data. Finally, we need to pay attention to R-squared from the output of summary. R-squared is an important measure of performance of the model. First, we will compute the variation of y without model, which is a sum of square deviation of observed y from the mean of y. We denote it as SST. Then we can compute the sum of square deviation of predicted y from the mean of y. This is a part of variation of response that can be explained by the model, which we denote as SSR. If SSR is larger, the difference between our prediction and the mean of y is larger. It means that our prediction is significantly different from the mean of a response, which is the estimated value of a response without a model. There is another variation, SSE, we mentioned in ordinary least square, which is a sum of a square error. It is a variation of a response that cannot be explained by the model or predictor. With a mathematical calculation, this equation holds true. We want a good model in the sense that most of the changes of our target or response variable can be explained by our model. In other words, we hope SSE, the variation unexplained, can be relatively smaller. In simple linear regression, we use R-squared to measure the percentage of explained variation. In our model for median price, R-squared is equal to 0.484. It means that about 48.4% of variation of MEDV can be explained by our model. Some may ask, is R-squared equal to 48% too low, and the model derived is not a good model? We will discuss it in more detail later. Here, please notice two facts. In this example, R-squared is less than 50%, implies the median price is not uniquely determined by a number of rules. There is a big portion of it explained by other variables, which we need a multiple linear regression. Secondly, if the response is very noisy, like stock return, R-squared equal to 48% is already high enough to generate profit in trading. We will cover these 2 points in multiple linear regression using stock market data.